Okay, so we are going to start. So we will have 4 presentations in this session focused on how to extract physical parameters from large scale, often complex and hyperspectral data with techniques covering the extraction and the identification of lines, and also the interpretation of gas kinematics in connection with star formation. And we are starting with the first presentation by David Cornu from the Lux Laboratory. You are also a fellow at the Prairie Institute, Paris School of AI, and you are going to present us some deep learning techniques for source detection in hyperspectral data.
Okay, thank you. So do the people on the Zoom hear me well? Okay, great. So thank you for the introduction. So I first want to present the context of the work I will present today, which is the preparation of the square kilometer array. So as you likely all know, the SKA is a set of 2 radio-interferometers currently being built in Australia and South Africa. Je monte le... Merci. Okay, so this is a huge instrument, and this instrument will produce a huge amount of data to a new scale. We are talking about 1 terabyte per second of raw data coming out of the instrument that need to be processed in real time on site. And we are talking about 700 petabytes per year of scientific data that we will need to store and distribute to the community. So the problem we have is that most data pipeline and algorithm don't scale well to these sizes or data volume. And this is an issue we have with most modern instruments. Actually, it's not that specific to the SKA. So I will indeed talk about source detection. So source detection is basically the first thing you might want to do on new images that you gather, typically from surveys of large portion of the sky that you obtain. And it's the concept of extracting a catalog of interesting objects, astrophysical objects, from the images. So basically, you want to separate the signal that is coming from the sources from the background noise and all possible instrumental effects or artifacts. So source detection is basically as old as astronomy itself. At the beginning, we were pointing to objects by eye. And as soon as we could, we tried to automatize this task. But all the modern automatic tools, I will say classical tools, suffer for similar issues, which is poor scalability with the image size and the dimensionality, especially if you want to process typically PPV cube, for example. And they most of the time expect a relatively simple source morphology, so they are trying to decompose the sources into single Gaussian or sometimes a few Gaussian component, which might impair the characterization of more complex morphologies. So this issue of scalability is well known, especially in the context of the SKA, and this is why the SKAO Observatory has designed a set of science data challenges that are made of simulated data that should resemble what the typical SKA data product will look like. So the objective from the perspective of SKAO is to prepare the astronomical community and to stimulate the creation of new innovative data analysis pipelines. So as I said, the first thing we want to do most of the time with our data is source detection, and the first 2 challenges were exactly about galaxy detection in either continuum images for the first challenge or in H1 emission cube, hyperspectral cube for the second challenge. For the third challenge, they moved away. They tried to tackle the reconstruction of the signal of the epoch of reionization, and I will not talk about that today. So our objective in our team at the Paris Observatory with a few other colleagues in France was to create a new detection method that is based on deep learning for object detection that will work on both these datasets. So there are plenty of family of deep learning approaches for object detection. We can classify them into 3 main families. So you have I would say the segmentation methods that belong to the UNet type of backbones. This is the top family here. So basically, you are trying to reconstruct a segmentation mask of your object of interest. Those are very praised in astronomical application because they produce masks that resemble the typical output of classical detection methods. So you can add on top of that whatever post-processing you already have for your classical method. But they are relatively slow because they need to process a lot of information near the pixel space level. Then you have two family of methods that are based on detecting bounding boxes. So in computer vision, a bounding box is the smallest possible box that contains all the pixels belonging to a given object. And we have the first family, which is called the region-based methods. We also call them multi-stage detectors because they will try to decompose the detection task into simpler tasks that are done by individual models. So most of the time you have what we call the region proposal models that will find region of interest in the image, and then you have a secondary model that will filter what is considered to be a good detection, it will refine the bounding box, and it will perform the classification. And then you have the last family of models that I think is a bit more interesting for our application, which are the regression-based model or single-stage detector. This time you have a single feed-forward neural network that is able to predict all the possible bounding box in a single forward pass through your network. And this is explicit just by the name of those methods. So for example, you have the single-shot detector and the you only look once. So they really emphasize the fact that you only perform one inference step. And those are very fast or very data efficient if you want, as they are widely used for real-time object detection applications. So I will focus on the you only look once method because the method we developed is derived from this specific approach, and I can present it to you in the general way first. So a YOLO model is basically a fully convolutional neural network backbone that will learn to perform a mapping from an input image to an output grid. Here, every grid element maps a specific subpart of the image. And this grid element will be filled with what we call detection unit. And each detection unit is tasked to predict a possible object for which the center belongs inside the regions that correspond to this grid element. So typically, the blue box here might be detected by this specific grid element. So here, each detection unit will predict several properties for each box. So it will predict the center of the object, the size of the box. It will predict what we call an objectness score. To simplify, it's just proportional to the probability that the box contains an object. And you can add whatever characterization of your object that you want. In the classical model, you have classification on top of the box detection. And you have as much classes as you want, depending on your training data set. Two specific properties of this architecture. The first one is that since it's a fully convolutional neural network, your output is basically a cube. It's a 2D grid, and for each grid element, we have a set of parameters that correspond to the detection units. And since it's fully convolutional, it means that here, your grid is basically the last convolutional layer of your model, meaning that each grid element will share its weights for all the other grid elements. So you are basically applying the same detector at multiple positions at the same time, but sharing a lot of the parameters of the model. And another effect of this structure is that when you have your trained model and you want to apply it to a given image, you will always predict all the possible boxes in your grid. So you always have an output that looks like the middle image here. But what we can do is filter them based on their probability score. So most of these boxes are in the background, they don't represent any object, so they have a very low probability score. So here the probability is simply the thickness of the box. So if we filter the detection, we might end up with a case like this one, where we still have a few possible boxes per element. If we leave it like this, it will be considered as false multiple detections, so we need to remove them. And the classical way to do that is to use an algorithm that is called non-max suppression. So basically, we search for the highest probability box in our prediction, and we will remove all boxes that have a strong overlap with it, but that have a lower probability score. At the end, what we hope to have is a nice image, like the one on the top right, with one single box per object of interest in the image. Okay, so this is great. This works well for everyday life images. But as you all know, astronomical images have nothing in common with everyday life images. There is, in fact, in this type of method, a lot of assumptions and bias that are baked in the method design that expect your image to respect some specific properties. In contrast, in astrophysics, typically we have no sharp edges for objects. It means that the bounding box definition is quite shallow already. We can have source blending, so when two objects are close to each other, they accumulate their signals, they will not obscure each other. We can have disjoint objects on large scale. We can have extreme density, and the default YOLO approach is known to be not very performant in a high density context. We have huge dynamic range, and we can work at high noise in high noise context. So for all these reasons, we took YOLO more as an inspiration, and we reworked everything we could about this method to make it specific for astronomical data and to our specific needs. So I will not enter into the details of our implementation. You can go see this paper, but the main idea, the main advantage of this new method is that we are able to reach sub-pixel positioning accuracy. We can be resilient to very high density of objects, and we can handle the large dynamic of the images. And the two main additions that are useful for the application I will show you just after is that we've added characterization on the fly. So it means that in addition to all the properties predicted by the detection unit, we add as many parameters as we want, which will help us to characterize our sources on the fly. So for example, predicting the flux, major minor axis of the source, position angle in the plane of the sky, or whatever you want that you can define in your training sample. And the second strong modification is that we have generalized all this formalism for 3D applications. So you can see that the method is named YOLO-CIANNA. It's because it's implemented in a wider framework that is called CIANNA. So it's basically our own version of TensorFlow or PyTorch that I've been developing since a few years. So it's a deep learning development framework, so you can train and deploy a variety of artificial neural network architecture with this tool. It's fully coded in low-level programming languages, including full CUDA implementations that allow you to accelerate using modern GPUs. And we support the vast majority of very modern architectural design in the GPUs that are dedicated to the AI applications. It's provided with a high-level Python interface. So if you are used to Keras or something like this, it's exactly the same principle. And it's compatible with a large wide of hardware because we have deployed CIANNA on both supercomputing facilities like Janzé, and it can be deployed on your laptop or even your mobile phone if you have some need for it. And this low-level implementation is what allowed us to make very strong modification in the way a typical YOLO regression framework would work and to specialize it strongly to our needs. So at this point, usually I do a live demonstration of a YOLO detector by pointing a camera in the room, but it's a bit time consuming. So instead, if you are interested in that, I can do it during the break. Okay, so moving to actual astrophysical application to our science data challenges. So for the first edition, it was about a large simulated continuum image of 33,000 pixels squared, corresponding to 1,000 hours of integration time with SKA. So it's already a quite deep image. And the objective of the challenge was to find the sources, determine their coordinates, and to characterize them, predicting their flux and their geometrical properties. And for this challenge, we were provided with a small fraction of the image for which we had the ground truth from the simulation. So we knew where the sources were, so we could train our method. And we then applied the trained model to the whole image. Just to give you a glimpse of our architecture, we will not review that in details. It's just that it's a custom neural network backbone. And you can see that it is composed of 17 convolutional layers for around 30 million parameters. So for those of you who are aware of the typical model size Today, it's very shallow. Okay, it's a very light neural network model compared to modern standard. And as you can see, we predict 5 additional source parameters, meaning that we can characterize our sources. So training this model on a single GPU is about 4 hours of computing time. And what is more interesting is that applying the model to the full 33,000 squared pixel image takes about 8 seconds on a single GPU. And again, this is to put in relation to the fact that this image required 1,000 hours of integration time with the SKA. It would require this amount of time. Okay, at last I show you some results. So this is a subfield of the SDC1 image, obviously one that our model has never seen during the training phase. It's the same field on the left and on the right. On the left, you have all the detections that are considered to be matching a source from the simulation using the challenge criteria. And on the right, you have everything that is considered a mistake by the network. So we can just consider that it's working quite well. And if we investigate the network errors, for example, the false detection in purple here, if we look at them carefully, in most cases, we have a source there. It's just that the predicted flux is overestimated compared to the true flux of the source. And it's rejected by the matching criteria just based on that. And in most of the cases, it's sources that are very faint and very close to the noise. So our model obviously cannot predict a flux that is lower than the noise. And for the green boxes, those are objects that should have been detected because they have sufficient flux. But in most cases, they are blended with an object that we already correctly detect. And they are often too close to be properly separated. So it's returned as missed object, but any method would have done this mistake in this context. Okay, I want to switch to hyperspectral data, so I will not develop that too much on the continuum images. Just to tell you that with this model, we have more than doubled the score of the team that originally won the challenge in 2019. And at this day, it's still the highest score on this dataset. But those are free data. Feel free to try it for yourself. Okay, hyperspectral data now. So in the second data challenge, we were provided with a large cube of H1 emission corresponding to 2,000 hours of integration time with the SKA. So it's a large 1 terabyte cube. This time we are provided with a smaller cube on the side to train the model on which we add the ground truth catalog, but that was produced with the same simulation code and in the same conditions. So here the idea is that we want to detect the sources in 3D, so position, frequency, and we want to characterize them again by predicting the flux and the geometrical property in 3D. Here you can see that we use a similar neural network backbone, but the main thing to notice is that everything is generalized to 3D. So we start with 3D cubes, slightly more elongated in the frequency axis. And we use full 3D convolution from the input to the output, meaning that our YOLO grid is a 3D grid, which means that it's actually a 4D space to predict all the detection unit per 3D grid element. So here, training this model takes a bit more time because it's heavier to compute. So it takes around 12 hours to train on a single GPU. And with this model, we can perform the detection on the full 1 terabyte data cube in around 30 minutes. And this is still vastly dominated by the time we need to load the file from the file system, actually. If you look at the raw GPU computation time, it's around 15 minutes. And again, this is to put in contrast with the 2,000 hours of integration time it would require to create such cube. All right, so I can show you quickly some results we get. So here you have a few sources that we have target using the ground truth catalog. So on the left, you have position plot where we integrate along the known size of the source in the frequency axis. And on the right, you have position frequency plot, and we do the same. We integrate over the known size of the source in the missing position axis. So on the top, you have what is considered the brightest source from the catalog. So this one is quite visible by eye, even if you don't know where it is and you don't know where you should average, you can still find it in the catalog. But there are maybe around 20 sources that you can find this way, which are very bright, and the vast majority of the sources that we are able to detect are actually more similar to the two bottom examples, and we have even fainter ones than these examples. So if you don't already know where the source is in order to stack the challenge around the source, it's very difficult to find it. So most classical algorithms, we completely miss these objects. So what we observed is basically that our model is able to create 3D reprojection of the source and apply them dynamically to the whole cube we provide. And we can verify that by reprojecting each of these source using their geometrical properties that we know from the ground truth catalog in order to maximize the signal-to-noise ratio we will obtain by averaging the channel, typically. And you can see that in this representation, they are way more clearly identifiable. And if you try to run a classical model on that, you will find the same sources that our algorithm is able to find. But the idea is that it can do that on the fly without any prior knowledge about the source distribution. So now I can speak about the statistical results. So as I said, there is around 20 sources that you can identify by eye. We are detecting more than 30,000 sources in this data cube with this method. So here you can see in the first line that we have actually won the second data challenge edition, because this time we participated. And since the end of the challenge, we have even improved the method slightly, and we have increased the result by an additional 10%. But what is more interesting, I think, in this leaderboard is the type of methods that were used by the different teams. So you can see that SOFIA is the only classical methods that were used by all the teams. The only team that tried to implement a new classical method, a non-statistical learning method, is the SKAO team that reached the last place, unfortunately. And the second thing we can notice is that the two top scoring teams here are using machine learning, but specifically 3D convolutional neural networks, which highlights the strength of this type of architecture to extract the signal we are interested in. But you can also notice that machine learning methods are spread all over the leaderboard, meaning that if you take a model on the shelf and try to apply it to this data, you will have nothing at all. You need to have strong knowledge of your target data if you want to adapt the method. Okay, so this is great, but all of this was about simulated data. What can we do about real observations? Because of course, simulations are not realistic enough, especially regarding some artifacts that we observe in the data. So those are typically deconvolution residuals here. And there is a strong domain shift from the simulation to the observation. So how do we train our method on real observations? We can use different techniques. So either we can use still simulation, but we will need to improve them by quite a lot. We could use classical detection method on real data and try to train on that, but we might inherit the bias of the classical method. We could use citizen science. For example, we have the Radio Galaxy Zoo project, where people are manually labeling the data, the images, and we could try to use that for training as well. Or we could try to combine all of the above, hoping that all the bias and specificities will compensate, but we have no guarantees of that. So the methods that we prefer are the two last ones. The first one is bootstrap learning. So we train a first model with not that well-defined training sample. We perform the prediction on the data, and we look at the candidates. And then we either do follow-up observation, cross-matching with another survey in another wavelength, for example, in order to confirm or infirm the different candidates. And then we reinject that in the training sample. So we have tested this approach in the context of the SDCQ, and it actually helped us to improve the results a lot. Or we could completely try to move away from supervised learning and use a self-supervised method, for example, more as a pre-training step on the data that we want to target themselves, and then still do a small supervised learning refinement at the end using either simulation or labeled observations. So just to show you that we are actually working on such applications. So we have 2 PhD students that are working on that. So we have Adam Zarka that is working on continuum surveys, generalizing the method to continuum surveys. And we have Adrien Hunter that is working on generalizing the method to H1 surveys and specifically on LUDMA. And I can show you a very quick glimpse of their preliminary results. So here you have a subfield of the LOTS DR2 survey. So you can see that there is a huge density of sources, but we are quite satisfied with these results. So here we train on synthetic data, but that are tailored for this specific survey. So basically we use the same simulation suite that were used for the SDC, and we modify all the information so it can be run for the LOTS. So of course, we still have very typical issues. So we still fail to properly detect the AGNs as a single source. We have a bit of artifact that remains, and very large sources that are not represented in our training sample are not recovered well. But this is very a preliminary result. And on hyperspectral cubes, we have first results from Adrien on the LUDMA cubes. And what we can say is that we are matching almost all the sources detected by the SOFIA software, but we have also new candidates, and these new candidates, a significant fraction of them have been confirmed with spectroscopic redshift from other catalogs in the same area. So we are quite confident that our method is able to detect new sources in H1. Okay, and I will stop there so we have some time for questions.
Thank you, David. Questions? Yes. Oh, the microphone. Sorry.
Thanks for the nice talk. I think I know the answer to this question, but I'm going to ask it anyway. So I was quite interested if your method could be adapted to, so a lot of the sources are quite compact, obviously in position space, but extended in position velocity space,
yeah.
Right? But could your method be adapted to, say, find particular types of sources in more complicated regions? So, for example, looking in molecular clouds, can you look for particular features in molecular clouds?
Yeah, we can. We actually run the method on the cube from the SDC3 challenge. So that was not about source detection, but on which they have added diffuse emission on top of the sources. And we were able to properly separate the sources from the diffuse emission. So if you're looking for specific features inside a larger signal or a more complex signal, it can definitely learn to classify what is interesting for you and what is not. The only thing is that you have to provide labeled examples first. Yeah.
Thank you for the very interesting talk. Just one question: when you were training for the hyperspectral source separation, in one of the next slides, you tested with images with the sources are in the center. So when you're patching your field of view, the sources you're training with, are they also centered in the patch, or are they like?
No, they can be at random position in the input. So these cutouts are actually not corresponding to the input size of the model. So the input size is larger than that. And here I have just centered it for the visualization. But the input is typically 64 by 64 by 256 subcube. And I think those one are a quarter of that, something like that. Yeah.
Maybe a quick one. What is the loss? Is it a multitask loss or something like this?
So the default YOLO loss will look something like this. So it's a regression-based loss. So it means that for the best match between the target and the prediction, we are moving the prediction toward the target. And for all of the box in the image, we are just lowering the score, the objectness score. And if we want our specific lots, it's a bit more complex, but I will not have time to delve into that, but we can discuss afterward.
Okay, so you have a kind of multitask.
Yeah,
loss.
exactly. We have a multitask loss, and it's controlled by different scaling parameters. So we can put the emphasis on the position, for example.